Hello, everyone. Let's go ahead and get started. I think most of you know me, but my name is Val Schwartz. I'm the head of admissions for NC State University's Institute for Advanced Analytics, home of the nation's first Master of Science in Analytics program. And I want to thank you for joining us today for the first installment in this season's Exploring Data Science webinar series, where our Institute faculty and alumni discuss careers and other hot topics in the field of data science. Our speaker today is Jim Box, who is a 2014 graduate of the Master of Science in Analytics program, and he works as a principal data scientist in the Healthcare and Life Sciences division at SAS. He's going to address human bias in machine learning and ways to mitigate that. He's going to present some slides and a demo for you, and after that, we'd love to have some discussion. But certainly if you have any questions throughout the presentation, feel free to enter those in the chat and Jim can address those at the end. So with that, I'm going to go ahead and turn it over to Jim.
Great, thank you, Val. Appreciate it. Thanks everybody for coming. Pretty much Val described what's going to happen today. We're going to talk about bias, sources of it, and think a little bit about our responsibilities as data science practitioners as to what's kind of going on here. So I always like to start this discussion by defining a couple of terms, right? And first off is, what do I mean when I'm talking about artificial intelligence? Because people use AI and machine learning sort of interchangeably, and they're really kind of not. And most times when people talk about AI, what they really mean is machine learning. But just to sort of drill down on this a little bit, right? AI is the whole concept of using a system to emulate human tasks. And you can see that machine learning is part of that. It's part of how AI learns how to do things. It doesn't have to be involved at all. You can make an AI system that's completely rules-based that never learns anything. I mean, we've been using those for years. Anytime you called up somebody on the telephone and they tell you to press 3 to talk to somebody, that's essentially an AI system, right? What we're really looking for, though, is on the machine learning end of things, right? So in machine learning, that's kind of the branch of AI where we're focusing on the idea that a model, an algorithm, some sort of automated process can look at data and make decisions on it. Why are we talking about this, right? Well, the reason we're talking about it is because these sort of systems impact us in a variety of ways in life. Sometimes you know about it, sometimes you really don't, right? Big thing in financial resources has sort of always been deciding, are you going to get a loan? What loan rate are you going to get? What other sort of products does this place have that they might offer to you? It's used a lot in criminal justice to the detriment of a lot of people, right? It's used a lot to determine who should get a harsher sentence, and it's really used to try to predict recidivism, to try to figure out, okay, if we release this person from the prison system, are they likely to recommit a crime? And we'll talk about that a little bit later, but that's very problematic. Happens in healthcare a lot. That happens to be my area of expertise. I spent a lot of time talking to healthcare and life sciences organizations. It can be used to determine treatment plans. It can be used to determine if you're going to be in a managed care program and what kind of care program you're going to have. We're going to see some examples where it's been badly used in life sciences. Happens in HR all the time, where they're trying to figure out how they're going to promote people through the hiring process, or who's at risk for leaving the organization. So maybe we'll try to mitigate that a little bit earlier and make a better offer to it. Big in the news this past couple of years, we've seen this, that everybody was deploying an AI tool to try to figure out what people were most likely to catch COVID, right, or have the worst sort of outcome to it. AI systems were built all over the place. This is an article in the MIT Technology Review, and kind of pointed out that they all failed, and it was pretty obvious that they were all going to fail. And we'll talk a little bit about why some of those things failed and what could be done a little bit differently. But I want to kind of break this up into 3 sort of groups. So typically when you're doing machine learning, there's 3 sort of big parts to it, right? There's the input data, the training data, the data you're using to teach your model how to make distinguishing things. There's all kinds of cool algorithms. There's always another algorithm. Somebody's working on their PhD right now, and they're going to put out a R package or a Python package that has some sort of crazy algorithm in it. There's always new and exciting algorithms. And then what you try to do with this training data and this exciting algorithm is come up with some sort of prediction typically. A lot of times it's yes, no, this person will have has the disease, doesn't have the disease, or how likely they are to do something. Could be a forecast that says, this is a demand forecasting thing, or a timed event sort of thing where you're doing a survivor sort of forecast. Recommendation engines happen all the time. Oh, you liked this movie, you should like this movie, right? Decisions, stepping you through a tree or showing you something new based off what you've already said. These are all the sort of things that happen. And so these are the three main areas in machine learning. So there's three main areas where bias comes in. And to me, the most heinous one, and we'll talk about it, is on the input data. So if you have biased data, which if you have data that's been collected on humans by humans, you have biased data. So when you have biased data, you're going to get biased results. These algorithms that are being developed are really kind of cool, but you have to be very careful when you're applying them because they're going to do exactly what you tell them to do, which might not be what you meant them to do. Okay, algorithms, no matter how cool they are pretty freaking stupid and will do things that surprise you. And finally, when you're looking at how you're doing these predictions and forecasting, if you sort of try to bring new data that the model wasn't trained on or the algorithm wasn't trained on and apply this new data to this algorithm, you might get some really weird results, but the model is going to look like it's very confident. So we're going to do some examples of each one of these. And let's start with the training data, because again, I think right now this is the biggest problem that we have. Let's use an example. It's probably the easiest way to do this. And we'll pick on our friends at Amazon, although I could have picked on a whole bunch of different people on this. In fact, this use case is really one of the first use cases that happened in the 70s when people started using these sorts of AI systems to determine who should be allowed into our program. But Amazon gets a whole bunch of applications whenever they post a position, right? And they have thousands of positions that are open. They open them up, they get hundreds of people applying for these. There's no way HR can look at all these things, right? The volume is just too high. But in about 2016 or so, Amazon said, hey, you know what? We're good at ranking things. That's what we do. We put ranks on things and we promote things up and we say, oh, we think you'll like this thing. So what they did is they built an AI system to look through all the resumes that they're getting in. They look at all the resumes of all the people they hired in the past and try to say, well, let's build a system that can rank these people that we're potentially looking at, kind of compared to people that we've hired, and sort of rate them on stars based on that. And then what we can do is focus on having HR screen and do the interviews of just the 5-star candidates, right? Makes sense? What could possibly go wrong? Well, obviously I'm using them in a case for bias. So in this particular case, went wrong is the first thing this algorithm did was throw away all the women, right? Why did it do that? Well, it did that because Amazon had a history of not hiring women, right? So just that fact is pretty bad, but let's look and see what it actually was doing. And we're using an example resume of my friend Elena, who works on this, does some of this work with me here at SAS and kind of comes up here. So here's her resume. If her resume went through this system and started looking at it, and again, it's been trained on data that completely overrepresented men. So this thing has a really strong bias for men. Of course, the first thing it did was notice that she had the word women's on her resume, right? If it just said chess club captain, it wouldn't have been a negative. But because it said women's chess club captain, the algorithm said, oh no, this is a problem. Did the same sort of things with names, right? Anything it could do to, and again, we're not even getting to the problem of assuming somebody's gender, right? That's a whole different issue. But anything it could do to figure out people it thought were women, if it had references to, her, she pronouns, it flagged them and got rid of them. Okay, and to their credit, Amazon noticed this, said, oh, wow, we're not getting women in here. What's going on? And so they were able to do things like, you could build in ignore lists. So it ignored certain words and phrases and that sort of thing. So they're like, okay, we fixed it. That was a problem. It didn't like women. We fixed it. Well, the next thing it did is it picked up sort of secondary indicators of gender. And in this particular case, it was because Smith College is an all-women's college, right? So the model was able to figure out, okay, these are not schools we ever hired anybody from. Again, we didn't hire anybody from them because we weren't hiring women in the past. And it was able to sort of distinguish and discriminate based on that. Again, felt like something they could fix with a bolt onto the model and say, okay, well, don't look at these sort of things and that sort of thing. And then they run it through again. And here's, I think, where it gets really, really problematic, is it looked at the way women tended to describe themselves in the text on their resumes, right? So women tended to talk more about things like communication and team building, where the men tended to write more about, I've done data manipulation and feature engineering. And she has all these things on here. But this idea of communicating effectively raised the alarm to this model. It's like, oh no, you're a woman, yeek, right? And literally that's what was going on. And that's I think the real problem, and the real thing I want to illustrate is that models that are trained on biased data are going to get really good at applying those biases, even in ways that you didn't expect, and even in ways more efficiently than humans could have, right? Probably a human who wanted to throw away somebody who was a woman and just saw communicating effectively wouldn't have thought about that. The model sure figured that out, right? And that's the real big problem, is that algorithms are going to be really good at that sort of thing. They're fantastic at separating things into two piles, right? All kinds of algorithms do that, but it's really important to sort of understand that. So as data scientists, or even as consumers of this sort of thing, we really need to think about questioning the data, right? Where did this data come from? How representative is it? How do we know it's representative? How did it get labeled? How did we decide what was a success and what was a failure? Like in this particular case, should they really have looked at finding people who are similar to people they've already hired? Well, no, they've been hiring dudes. Maybe what they do is they go through and find, here are the resumes of people who have been successful in our organization. Let's put those into this model to train it and see if we can find people that have those sort of characteristics. They still run into the same sort of issue, but maybe not as bad. And then is there a feedback loop? Is there a way to sort of mitigate these problems as you see them? But part of the biggest thing, the biggest challenge is, are you looking for it? Really, and that's kind of the whole point of my whole talk here, is that you got to be looking for this stuff. Right, so that's what we've got on data, okay? Biased data is going to give us biased results. It's guaranteed. There's no way it's not going to. Second part, we think about those models, right? We've got all these different cool algorithms that do stuff. The problem is they do exactly what we tell them to do, which is typically put these things into two different groups, right? That's typically what we're doing on these things. So here's an example. It's sort of famous. It's a little contrived, but I think it's kind of a cool example where these guys trained an AI, as a CNN, I think it was, to figure out if you could look at a bunch of pictures, is the thing you're looking at a wolf or a husky, right? So they gave it a whole bunch of images and said, okay, here we go. These ones are wolves. These ones are huskies. Take a look at them. I'm going to give you new ones. You tell me what these things are, right? And you can see the model was pretty good at it, right? It went ahead and said, yeah, 5 out of 6 times it was able to figure out who was a wolf and who was a husky. You might think what it's looking for are things like coloring, maybe the eye colors, maybe the shape of the snout or the way the ear sort of set up. But if you look at this, can you figure out what it was doing? Yeah, that's what it was doing. It was looking for the snow, and it was looking in the background. It was looking for some of the secondary characteristics in those pictures. And it realized, oh, all the pictures you gave me of huskies, they were inside or outside in the grass, or maybe had a frisbee with them. And everything we had of a wolf was outside stalking something in the snow. And so the model sort of figured out, oh, here's the easiest way for me to break these things up into two groups, which was exactly what you asked it to do. So the algorithm didn't fail. It didn't do what you expected it to do because you didn't think about it enough. That was a silly example. Here's the one a little bit more problematic. So here's a study that these guys did. They got the link there at the bottom about looking at using images to sort of automate some radiology, right? When you're in a hospital, or if you're in a clinical trial, you get a lot of images, and you have one of the big labor intensive things is having a human look at these images and saying, that one's got a problem, that one's probably okay. This one we need to look at and maybe do treatment 1, 2. This one is maybe treatment 2. And so what they were going to do is say, okay, can we train an algorithm to look at a whole bunch of these images that we have and see if we can diagnose who has, in this case, it's an enlarged heart, right? So that's what they're looking at, and kind of the size of the heart could lead to some sort of bigger sort of problem. So they fed it a whole bunch of trained images, or a whole bunch of labeled images about who had the condition, who didn't have the condition, and even had them sort of rated as to how bad it was. And so they then would say, okay, instead of having a human look at these, what we'll do is we'll have the first run of these images go through this algorithm, sort them, pick out the worst cases, and have our radiologist look at those, right? And kind of not worry about the other ones. And so in this particular case, this is what it did. So this patient actually has the condition. They have a bit of an enlarged heart. The model gave them a probability about 75%. So, okay, seems like it's working, right? Seems like it did a pretty good job. If you take a closer look, though, one of the things you can do with some of this, and it's really tricky with images, a little bit easier when it's numbers and data. As you start putting in images and text, it gets a little bit harder. But one of the things you can do is look and see, okay, how is it making this decision? You have to put some effort into doing this, but these guys did that. And they said, okay, let's look and see what parts of the image had the biggest sort of impact on what the outcome was. And what you expect to happen happens. It's looking a lot in the chest area. It's looking at the shape of the heart relative to maybe the width of the sternum, or where it's sitting in the rib cage, or distance from the clavicle. It's looking at all these sorts of things, which is what you expect it to do and what a human would be doing, right? We'd be looking right around those things. However, it was looking at some other stuff too. And I don't know if you can see the words in there, but the big thing there is in the upper right-hand corner is the word portable, right? So it's a tag on the image itself that was taken. It was sort of a metadata tag. And what this was it was a portable X-ray machine. So one thing the model learned to figure out pretty quickly was that, oh, if this image was taken by a portable X-ray machine, that tends to be somebody who's pretty sick because they can't go down to the X-ray machine. So what the model was able to figure out pretty quickly was that sick people are sick, which is factually correct, but not particularly helpful or useful, right? Some of the other things that was happening are some of the non-visible metadata tags that were in this image, right? Because these images come with honestly, they come with an XML file sort of attached to them. And it was, the model was actually looking at things like, who was the reviewing radiologist on the original image when it was training it, and it was picking up that certain radiologists saw problematic patients more frequently than others. Again, if we didn't stop and think and look at this, we wouldn't have noticed. We just would have seen, oh yeah, this thing does a pretty good job of this. In this particular case, here's a woman who also has the same condition, but you'll notice up there in the upper right-hand corner, the model actually downgraded her a little bit because it didn't say portable. So it lowered the probability that she had this condition, even though she does, because it didn't have the thing in there. And it's really important to understand, and it's a little blunt to say it this way, but models are lazy. They're effective, but they're lazy. If you're not very careful, they're going to do exactly what you tell them to do. Break these up into two groups. Tell me which one are sick. Tell me which one isn't sick. Break these up into two groups. Tell me which one the wolves are, which one the huskies are, right? The model has no concept, and I say model algorithm, same thing, has no concept about context unless you specifically tell it about context. All right. With the wolves and the huskies, what we could have done was, grade out the background, use this zoom image blur kind of nonsense on it, and grade that out, and then run the algorithm through so that it was focusing more on the animal itself, right? So our responsibility is to actually think about this and question the results and try to understand, why did the model make this specific prediction for this specific case, right? So when you see this model said it was 75%, don't just stop there, right? Ask, query, why? Why did it say this, right? And you'll learn some interesting things. And this is a lot of stuff you have to do sort of in conjunction with a subject matter expert. And you might surprise a subject matter expert with some of the things you find in the results of one of your models, something they maybe hadn't thought about. But if you present that to a subject matter expert and they can't figure out, okay, I didn't expect that, but it makes sense. If you don't get that response, there's probably a problem, right? It's okay to surprise them, but it shouldn't perplex them, right? So it's really important to understand. It's really important to understand what exactly was the model set to do. Think about a model like a 4-year-old, right? You tell her that while she's sitting there eating dinner, that unless she clears her plate, she's not getting any dessert, right? And then you turn your head and you go put things away, and you turn back and the plate's clear, and you're like, hey, yay, great, here's your dessert. Well, you don't notice a dog underneath the table, eating all the food she just dumped on the floor, right? She did what you told her to do. She cleaned her plate. That wasn't what you meant for her to do. You meant for her to eat everything. but you weren't specific enough when you did this, and you didn't provide specific context. So the model took the easy way out. The model always takes the easy way out. That's what they do. Okay, so you have to just be aware of that. Again, I really sort of wish we had a cool ribbon color, right, for awareness of this kind of stuff, because that's really what I'm sort of plugging here, is that if you're not careful, the stuff's going to look like it made really good sense. It's a big, big problem now as things get more and more automated, right? As they're starting to pull humans from putting hands on keyboards to figure these things out and turning into a big black box, when all you're looking at is the, percent that it was right, or the misclassification rate. If you're not thinking about it, you're going to accept things that don't make any sense. There's actually a term for that. It's called math washing, and it's really heinous. You can read Kathy O'Neill's book, Weapons of Math Destruction, to look at some of the real problems with that. All right, number 3. Models only perform well on data they've been trained on. Okay, so really, when you've built this really cool algorithm, you've gone through, you removed some of the bias stuff that you have in the training data. Maybe you've done some oversampling to help mitigate that sort of thing. And then you've got a prediction, so it's coming out. It looks like it's a good prediction, but again, if this data is not like what the model was trained on, you could have some issues here. And I'll go back to my friend's, I guess she's going to turn 4 on Friday, Elena's kid, right? So she sat down with her kid and was showing her picture books of animals and trying to help her figure out how to identify animals, right? Look, here's a dog. Look, here's a dog. We're not even getting to this one's a pug and this one's a golden, just dogs. Here's some dogs. This is a dog. This one's a bunny, right? So as a kid starts looking at these sort of things, they start to get some sort of thing going on in their heads about, okay, how you distinguish between a dog and a bunny? Well, if I'm just looking at these sorts of images, it might be something as silly as, well, the dogs are always facing me, or the dogs have their tongues hanging out, or their ears kind of go down where the bunnies go up, or dogs sit with their paws really close to each other, right? There could be a whole bunch of ways that your kid's learning how to do this. But then when you show her some monstrosity like this thing, she doesn't know what to make of it. Is that a dog? Well, it's kind of sitting like a dog. Is it a bunny? Well, it's got kind of the side view and it's got the ear sticking up, so maybe it's a bunny. When I was doing this presentation for my internal group, one of them actually had their 3-year-old sitting on his lap while she was just sort of watching this, and he asked her what it was. She said it was an elephant. Okay, sure, maybe. But the problem here is that you're exposing this model to something that is completely different than the data on which it was trained. And that can be a real problem, right? There was a thing at the Institute last semester where they had the women in data scientist group come in and talk, and one of them was giving this example of an image recognition thing that was done that was supposed to try to figure out what kind of clothing a person is wearing, right? So distinguish between, this person's wearing a blouse and a skirt versus, some sort of suit. And they trained it on thousands of images from some standard image database. And when they put an Indian woman in a sari on it, it classified that as a costume. Why did it do that? Well, the training data, even though people from India make up about 18% of the population of the world, in the training data, they made up about 4% of the population of the world. So for the Indian woman, who this is what she wore on a Tuesday, the model thought, ooh, this is a costume, right? Because it was being applied to data that was very different than the data it was trained on. A bigger problem in healthcare, and this happens a lot, but the National Health Service has this really big genomics database, right? That they've captured genomic data. They've done some DNA sequencing on all the different people that are sort of patients in the National Health Service. And they were using that to try to figure out if they could use genetic screening to help do things like predict susceptibility to schizophrenia. And what happened, what it turned out to, is that it was taking somebody who was from Africa and giving them a 10 times higher probability for having schizophrenia than a similar person from Northern Europe would have happened. And the problem there was that most of the genomics in the database were taken from people of white Northern European descent, right? So the model was then exposed to some genomic data that it wasn't really familiar with, and it made a prediction, and these predictions were very traditionally 10% higher. Had nothing to do with actual prevalence of the disease in the population. It's because you were applying a model that had been trained on white people, white Northern European people, to people of African descent, right? These sorts of things are going to happen. They're guaranteed to happen, right? This is a 100% guarantee this is going to happen unless you're looking for it and thinking about it. So again, your responsibility on this is to figure out, is this data similar to what the model was trained on? The different groups in my population get different results, right? And I'm going to show some examples of that with something my friend Hewitt did, where we looked at this, and we'll do a little show and tell here in a couple of minutes. And then is there some sort of human feedback loop that allows for retraining the model? We can't treat these things as black box systems, right? Even though it's much, much easier to treat them that way because of all the automated software that we're doing, right? One of the things we're doing in data science is we're automating ourselves out of jobs because we're creating all these really cool things that do this. One of the places you can bring value is by saying, whoa, pump your brakes. Let's make sure we're understanding how this thing works, right? And this data that's being trained, right? One more example, because it just occurred to me to think about, is, there's a lot of AI systems being trained on auto driving cars, right? And one of the ways they do this is they train it on simulation. So they don't like take a model out and have somebody sitting on it and driving around and catching data. They sort of simulate. They even use video games to sort of do this, So you're hoping they're not using Grand Theft Auto, but they're using things like that. Anyway, one of the things they had done is they had trained this car on how to drive on the freeway, and that had worked. When they applied it to driving on the highway, the first time it saw a truck going sort of perpendicular to it, driving across its path, it T-boned it right away. Why did it do that? Well, in the way the model was trained, it was trained on the highway. What does a semi-truck look like to you on the highway? Looks like a big rectangle up here, right? Okay, so I know that that's a truck. I know I don't want to bump into it. When you're on the highway, what looks like a big long rectangle that you drive under all the time? All those freeway signs up in the sky, right? So what happened is when this trained driving simulation was applied to city driving, and it saw a truck going across its way like that, it said, "Oh, that's a sign. That's an exit sign. I'm just going to drive right underneath it." Right. So this has real problems for real people. So takeaways. Where do these biases come from? Well, they come from us, right? They come from a historical collection of data that was biased towards old white dudes like me, right? So there's all kinds of bias in this data. The models are going to pick up these patterns that we're not explicitly trying to teach them. Guaranteed, that's 100% going to happen, right? And then there's the lack of awareness by data scientists about how these historical and societal biases might be present in data modeling, right? Again, the people who have been doing these things for the last 20 years are people that look like me, so we have been able to be blissfully unaware of some of these historical and societal biases because they didn't impact us as much, right? Now, as we're applying these sorts of processes to more and more people, we're really sort of exacerbating the problem by hammering people with models based off these biases. So we need to think about this. We need to think about it especially when we're thinking about the training data, but we also need to think about it in terms of the problems we're trying to decide to solve with an AI system, right? Twitter had put together this idea of having a tool in one of their images things that said auto crop out the people, right? So they built a little AI system to automatically crop out people. The first thing it did when they tested it on a wide variety of images was it ignored all the black people because it had been trained mostly on white people. One of the things they realized was that, you know what, this really isn't a good candidate for AI based off the types of data that we have available to us. So why don't we just put in a little drag and drop thing and let people manually crop their pictures, right? So not everything needs to be an AI system, right? The data we choose to train the models on, how we're thinking about accuracy, and how we're presenting the results. These are all really, really important with how we're going to talk about that. So I'm going to do a little show and tell. And what we've got here is data on a bunch of ICU patients who have come in the front door, right? Now, again, we're talking about ICU patients. So a lot of times these are people that you can't talk to. You can't get a good medical history on. If a patient coming in has diabetes and you know about it, you'll treat them differently than a patient that doesn't have diabetes. So it's important to know, is this patient diabetic when I'm deciding what sort of treatment path to give them? If they are coming in a state in which I can't ask them that, there's no quick test for diabetes, right? A lot of these things, what has to happen is some results have to come back from a lab, and it might take a few hours to get this back to figure out, okay, is this person diabetic or not? So what we have is data on the first 24 hours of intensive care for about 13,000 patients across the United States. Right? And this came from a Kaggle competition. Data we can get right away are some lab results, some demographics, and some vitals. Not all lab results come in right away. But what we want to look and say, okay, is our model working right? And the way that my friend Hewitt, who now works as one of the responsible AI people, she's a graduate of the program, by the way. She's like one of the head people in the responsible AI at Microsoft now. She kind of built this demonstration with the idea that she's gotten some feedback that the model isn't performing well for certain demographics, which in one case, it's good that we're looking at that. I'm going to return to my application here. It might take a second. So I'm going to show you some data and some report that we might use to help us understand that. All right. I obviously talked too long because everything closed on me, but we'll see what happens here. So again, we're looking at trying to predict diabetes in the ICU. The training data we had 130,000 patients that came in, about 22% were diabetic. And we had slightly more males than females, actually probably significantly more. So we had 50% of men and 45% of the 130,000 were women. Most of them were white people, which probably is okay. About 10% African, about 4% Hispanic. So the first thing we want to do, again, we're trying to train a model. Maybe the model's not working well. One of the things I want to look at and say, how representative was our data, right? And so over here on the left-hand panel, I've got some demographics of my training data. And over on the right, I've got the demographics of the public in general, right? So we've got some sort of historical data, some sort of idea here. You'll notice that basically we're looking at 7 to 16% of people, somewhere in there, depending on what state you're in, are diabetic. We're using type 2 diabetes here, are diabetic. In our population, it was like 21%. So our population in the ICU is a little bit higher, which may or may not be an issue, right? Maybe it's just that these are people that go to the ICU more frequently. One thing we noticed was that, we had 54% men, whereas in the whole population of the country, it's pretty even, right? In terms of how many women and men there are, they're kind of showing up. And some of our breakdowns on ethnicity were a little bit interesting. I mean, we have 77% Caucasians in our data. That's about 76%, that's about right. But if you remember, I said we had, Hispanic. So we had 4% Hispanic in our population, whereas the population as a whole is closer to 9% Hispanic. So one of the things we might want to do is say, all right, can we figure out, is this a problem in our data? One of the things we did was look at this idea of AUC parity, equalized odds, and predictive parity across different groups, right? So AUC parity is what you think it is. It's the area under the curve for the model that we built to do the prediction. And you'll notice that for the females and the males, the parity was about the same. The area under the curve, if you just look at men and just look at women, it's about the same. So even though our population wasn't quite the same, the parity that we're seeing here, if it's like, makes me feel like, okay, it's not a big deal, right? Same of the idea of equalized odds, when we're looking at false positive rates and true positive rates, we don't really see a difference across the two groups, right? And in this case, we take the difference between 82.1 and 81.6. We look at the difference between these two. So our differences aren't that big. And the productive parity, the average predicted probabilities, predicting yeses, was about the same for men and women. So off the bat, I can look and say, all right, you know what? I don't feel like these binary gender distinctions are limiting or causing a problem. Is binary gender thing the right way to go? Probably not, but we won't even go in there, right? But that's what we can determine through here. If we look at this same concept on race, we see something a little bit differently, right? We see that there is a difference in AUC for the races, the way that we have the races set up. And again, I'm not even going into the idea of breaking things in races makes a whole lot of sense. But we definitely see some difference there. We see some difference in our equalized odds, right? The true positive rate and the false positive rates are different across different groups, right? First thing I might want to do is try to figure out why. Why is that? Some of it's going to be because the group sizes are varying sizes, right? The men and women were kind of close, similar in overall size, whereas when we look at the ethnicities, they were quite a bit different, right? So we might look at that. We might look into doing something like oversampling. Maybe the problem is we don't have enough Asians in our population. We might want to oversample them or undersample some other group. But what jumps out is that, okay, there's definitely something interesting that's going on here, and we need to think about it, okay? One of the other things we might look at are SHAP estimates, where what we're doing is we're trying to figure out for these different variables that turned out to be important in predicting if somebody was diabetic or not, do these estimates change much for groups, right? And so basically the orange line is the group in whole. The orange bars never change, even though the sizes are going to change a little bit because of the way the graph sort of rescales. The orange lines never change. The blue lines are whatever group I've selected. And right now I've selected everybody, right? So that's why these things are the same. If I say, well, let's just look at women. Changes a little bit, right? So there are some differences in some of the estimates. Some variables are more important in the women than the men. Doesn't really seem to be that hugely different, but it's something to look at. And again, we looked at men and women in a different way and felt like, okay, we're probably in pretty good shape there. But if we do something like, well, let's look at African American, what happens there? Well, the more interesting that happens is that some of these SHAP estimates change direction, right? And this is where we're going to want to start thinking about, why did this happen? And this is where you start to get your subject matter experts involved. Maybe it makes sense on glucose or creatinine. Maybe it doesn't. I don't know. I'm not a practitioner, but these are things that you're going to want to sort of ask about, right? We saw Hispanics were an issue in our data before. You see that the glucose is really different with Hispanics. And then the age was really different. Does that mean the population breakdown of the Hispanics that we have in our data is very different than the population breakdown of everybody else? It might, and that might be something we hadn't thought to look at, but we want to spend some time to sort of mitigate these things. The last thing I'm going to show you here on the show and tell, and then we'll move into question and answers, is this concept that a lot of times you don't want to use certain variables in analysis, right? Sometimes, like if you're in the financial world, you're required to not use certain variables. You can't use race as something that distinguishes whether or not this person is going to get a loan or what kind of interest rate they're going to get. You're not allowed to use race the way it's written, right? Sometimes you just might not want to. In this particular case, we said, okay, let's ignore race because again, what does it even mean? But let's not put race in the model and see how things go. Well, anytime you're doing something like that, anytime you have a problematic variable or a variable you're trying to think about, one of the things you really want to do is look at, do you have proxy variables in there that are going to predict what this is? So what we looked at was to see what we could come up with in terms of, can I predict somebody's ethnicity given all the other data I have on them, right? I don't want ethnicity in my model, so I took it out. So good, I did it. I got rid of ethnicity. I got rid of bias. Yay. Well, did I? Because one of the things I want to do is say, how well can I predict ethnicity, right? And in this case, I'm looking at African Americans. And you'll notice that African Americans represent, in my data, about 10.7% of the population. However, I can come up with a group that has a 65% chance of people in that group being African American. That might possibly be a problem. And so what we did is we just simply let this thing come up with its own model. This is actually doing a random forest in the background to figure out what variables do I have in my data that are actually highly predictive of ethnicity. In this particular case, it was looking at African Americans. And you'll notice, I don't know how well you can see this, but there's three variables up here. Two of them, one of them is ICU ID and one of them is hospital ID. What these are showing me is that if I know what ICU this patient was in, I can really well predict what their ethnicity was. Well, basically, I put zip code in there, right? Because in pretty much you're going to be going to the hospital for the ICU that you live most closest to. And what we found is that, wow, as in almost anything demographics, if I know the first three numbers of your zip code, I know a lot about you. And that's what we're showing here, is that it turns out that if you know what ICU these people are in, you know what their ethnicity is. Does that even make sense to include those in the models? Probably not, right? Why would ICU ID have anything to do with, is this person walking in the door, have a problem with diabetes, right? So maybe I don't want to include those things at all. But the one that was the most interesting is right here. And it's hard to read, but this is oxygen saturation. Okay. And what it turned out was that if you use oxygen saturation in conjunction with a couple of these other variables, you can actually highly sort of predict what the ethnicity is of a person, right? And it's showing you that if it's picking higher level oxygen levels, that it has a higher correlation with predicting somebody who's African American. And this is one of those things where you want to talk to your subject matter expert. And this is actually something that came up early on in the pandemic, where one of the problems was that people of African descent weren't being treated as aggressively for COVID, so they're having worse outcomes. And the problem is the way that blood oxygen level is measured, right? Anybody ever had their blood oxygen level measured? They clamp that little thing on your finger, right? That's a pulse oximeter. And what it's doing is it's sort of shining light through your skin, and it's kind of measuring kind of the color of the blood vessels in there, measuring some light diffraction of the blood vessels in there, right? Well, maybe you can understand what's happening right away. It doesn't work as well on dark skin. In fact, it can be a problem if you have dark fingernail polish on. What happens is not the amount of light doesn't pass through is the way they were calibrated, because they were built on white people. And what it was doing was giving artificially high values of blood oxygen levels for people who are of darker skinned areas. So I might come into the hospital the same time my friend Hewitt does. We might actually have the same blood oxygen level, but her reading was a little bit higher. So I look at her and say, you're not struggling yet. We're going to put all our resources on this guy because his blood saturation, his oxygen sat went down, right? So it was artificially inflating the saturation levels for people with darker skin, which meant they weren't getting the treatments they should have been getting earlier on. And this became a well-known problem at that point. But these are things that you wouldn't know unless you look for them. Why does blood oxygen level help me predict the ethnicity of a person? Well, it turns out to be a flaw of the way the system is designed, right? So these are just some of the things that you might want to think about. I'll leave you with a couple of things, and we'll go on to question and answers. One of my favorite websites for looking at just how AI works and behaves in ways you might not think is this site called AIweirdness.com, written by a woman named Janelle Shane. She does some really cool stuff with AI. Her book, it's called If You Look Like a Thing and I Love You, is a fantastic book for understanding how AI systems work and do things that maybe don't make sense. The name of the book came from her training a neural network to generate pickup lines. And that was one of the pickup lines it came with. But just, it's a really nice thing to read. She's got some stuff in here about, she uses GPT-3 a lot to make cakes and stuff. She'll have this thing create recipes. It's just fantastic to read through what she's doing, right? So it's a really good thing. The book, like I said, is it's a really good book. It really explains AI systems and how they behave in ways that you don't sort of expect. She's got a couple of TED Talks out there and some videos. She's really good. And the other thing I recommend is this movie right here called Coded Bias. I'm pretty sure it's still available on Netflix, and it's kind of written by a woman, or it's not written. The star of it is this woman named Joy from MIT, who was doing some facial recognition work in her PhD program, and realized that when she was pointing her face into the camera, it wasn't recognizing it. But she had this weird white mask next to her, and when she put that up, ooh, it worked. And that got her thinking, and it got into a whole bunch of different things. And she's testified before Congress talking about these sorts of problems. So it's a fascinating movie. Joy herself is really interesting. She's got a good TED talk out there. But go out and find ways to sort of educate yourself about what's going on. So that's my soapbox. I would really like to hear if anybody who's working in an organization right now, if your organization is thinking or talking about this, or any thoughts that you have, or any questions that you might have. So I'm going to sort of open the floor. Just, take yourself off mute and say something.
So I guess I'll go. There's a space here to talk.
Sure.
So you found that implicit bias in this example. What was kind of first steps then that you took, knowing that there was bias in that data? What do you then go and do?
Which one do you mean?
In the hospital diabetes scenario.
So part of it is understanding, okay, it might be something as simple as, well, let's exclude these hospital IDs and from, if we're trying to predict gender, but let's not have those be variables that are in our model if we're trying to predict if somebody has diabetes or not, because they're not really helpful. Maybe what we did in the side of the Hispanics would be to oversample them, try to get our sampling populations kind of up to what's matching out in the world. Maybe we look at the ages, right? Because we did see that the patients who were coming in who are Hispanic had a different age platform than other people who were coming in. Part of this is who's willing to come into an ICU, who has access to an ICU. So it's almost having to think about the societal issues in there as well. One of the things you might wind up doing is making different models for different subgroups that are easy to distinguish, right? So maybe you make a completely different model for people of Hispanic background than you do of people who are African American background. There's a variety of things that you can do there. Part of this is discussing with your subject matter expert about what's reasonable. Part of it is looking and seeing what data do I have available to do that. But the bigger thing is just looking at this. Anybody else have questions or thoughts? One of the things we're doing at SAS right now is we've actually tried to put in, we've built a center for ethical AI. Other organizations have tried this and have had problems. Google very famously had a big problem trying to come up with an AI sort of governance board and how to address this. We're still sort of struggling with figuring out how that's going to be. Part of it is in our software solutions. We're trying to make it easier to see that, right? Just have some plain text that comes up when you do a model that says, here's why this particular prediction for this patient was significant. Here's why we're predicting this, right? I know that Data IQ has a whole selection on trying to understand bias and trying to sort of automate this idea of looking at your training population and trying to automate some processes around comparing training populations to other populations. Like I said, my friend Hewitt, who's a 2016 grad, recently left SAS to go to Microsoft to be one of the main people on their ethical AI. So there's a lot of discussion about this now, which is good. A lot of organizations are thinking about it, but it's really sort of incumbent on us as data scientists to sort of bring this to the table and make sure people are thinking about it. Because again, math washing is a very real problem. This idea that because the computer told me there can't be any bias, algorithms aren't biased, and they're kind of not biased, right? There's nothing inherently evil about the algorithm. The inherent evilness is in all the data that we've collected over times and the systems that we have in place in this country and other countries that lead us to this data. I will say that regulations are coming about how this stuff works, and is the case with anything with dealing with data privacy and this sort of thing. They're coming from the European Union first. There's a lot of work over there right now in trying to figure out what it means to be a victim of an AI system and what sort of rights that you have. If you watch the coded bias document, you can see them using facial recognition software in London to try to find people who have warrants on them. And a bunch of cops jump out of the van with guns and grab a 15-year-old who is wearing a school uniform. Right? Some cities like both Portland, Maine and Portland, Oregon have outlawed the idea of using facial recognition for any law enforcement sort of things. Right. So there are laws in place and rules in place. Like I say, Joy here in this movie talks to Congress about this a little bit. So it's going to become a bigger deal. Hopefully. I think it needs to be a bigger deal, and I think it needs to be something that we're thinking about. And honestly, I think this is a value that you bring to an organization as a data scientist, right? Because your biggest competition for jobs in the next 5 to 10 years is going to be a piece of software. Why would I hire you when I can just buy another seat of Data IQ and let it do stuff automatically? So part of what you as a data scientist is going to bring to an organization is the maturity to think about this and the ability to prevent something bad being done with somebody's software, frankly.
Hi, Jim.
Hey, Susan.
Nice to see you. Thanks for giving this talk. Dr. Simmons told us a couple weeks ago in class that you have done this at the Institute in the past, so I'm really glad we got the opportunity to hear this today. We could certainly take this question to, I could talk with you about this another time, but I know a couple of my classmates are here, so maybe they're interested in hearing this as well. You've talked about ethical committees at software companies. If we were interested in getting a job, having an impact with this in the medical field, do you have any recommendations of where we would look?
Wow, that's a really good question. I don't know the answer to that, right? I don't know what companies are taking that sort of seriously. I think you could sort of research an organization to see if it has a data ethics board. Hopefully hospitals and medical things will be they're most likely to be the first ones to kind of come up with this. I think banks and finances will lag that a little bit. But on the medical side, I think the regulations are going to sort of hit there first, because they typically always do, right? Yeah, so that's a good question. I don't really know, but I would definitely want to look at the organization, kind of research on their website at that, and I would bring it up in an interview, right? When they come in the end and they ask you about what kind of questions do you have? Well, how are you guys addressing ethics and fairness in how the AI systems are being used? It'd be a fantastic question to ask an interviewer. I have no idea what most of them would say, which would be fun. Yeah, I would actually use that as a question.
Well, if you think of anything, let me know.
Yeah, anybody else have any thoughts on that? Okay. Well, I think that about wraps it up then.
Yes, thank you so much, Jim. This was fantastic. I know I learned a lot. I think we probably all did today. We will post a recording of this talk on our YouTube channel, and I just want to put in a plug for our next Exploring Data Science webinar. Jim mentioned Data IQ a couple of times, and actually one of our MSA graduates who works for Data IQ is a solution engineer, Jing Zhao, from our class of 2012, will be our next speaker, and she'll be talking about some AI use cases. So sort of an expansion on what Jim's shared here today. So thank you all, and hope you have a great rest of your day.
Ask your questions about ethics.
Thanks, Jim.
See ya.